All right, so today we're going to take a look at section 1.1, which is a brief preview of calculus. The first thing that I want to talk about is a basic overall description of what is calculus. Calculus is really the mathematics of change. And the first kind of description of how things change we're going to talk about is two different kinds of lines. And you have seen these described before. So if you've taken calculus before, I want you to take a step back and pretend like you haven't talked about calculus. And for those of you who haven't taken it before, you don't have to pretend. So I want you to think about, where did you first hear about these terms, secant line and tangent line? Geometry, that's right. And you learned about them in reference to circles, right? Okay. So a secant line is a line between 2 points on a circle. So back in geometry, you drew things that looked like this. You found 2 points on a circle, and if you connected them, that was called a secant line. It cuts through the circle. The exact same thing is true when you talk about any kind of a curve. So when calculus, we're going to do things more on curves. In particular, we're going to do things on functions, which we'll talk about more later. But so we're doing the same thing, though. If we take two particular points on a curve, let me put it here, and we connect them with a line, that's called a secant line. That's all a secant line is connecting two different points on a curve. Tangent lines are a little bit different, okay? So tangent lines can be talked about as being a line that just touches a curve, right? So if you imagine a ball, like a basketball or a globe or something like that, and you put a piece of wood laying against it, it would touch it exactly at one particular point on that ball, right, or that globe. That's a tangent line, or at least a visual perception of what a tangent line would look like in 3 dimensions. So on a circle, it would look something like this. And it touches at exactly one point if we're careful enough in how we draw it. And the exact same thing is true no matter if we're dealing with a circle or a curve. So if we take one particular point on our curve, and we're careful, we should be able to touch that one particular point by drawing what's called a tangent line, and we'll talk more about tangent lines and how to draw them later. Yes?
Is it specific to curves, or could you have a tangent line on a square if it's touching the corner?
We'll talk about where you can and can't have tangent lines. On the corner of a square, you wouldn't have a tangent line, and we'll talk about why when we get to the point of actually creating tangent lines, which is a really good question.
Can you have a secant line on a square then? Or no?
You can have a secant line on a square. You can have a tangent line on a square as well, just not on the corners. Yeah. All right, so what we're going to talk about here in this section, remember the title was A Brief Preview of Calculus. We're not getting real in depth, and in fact, we're not going to do anything that's really calculus. But we're going to look at how calculus approximations can be used in calculus with calculus concepts. And we're going to do just 2 simple examples. They're a little bit time-consuming. They're a little bit detailed. And what I need you to do is I need you to have your calculator out if you have it with you. And if you don't, just kind of try to write down some steps for what I'm doing so that you'll know how to deal with it later. Okay? All right, so what we're going to do is we're going to estimate the slope of a tangent line. So I drew a tangent line over here, or at least roughly drew some tangent lines. And we can calculate slope on a tangent line. You calculate slope on any line using a slope formula. Do you remember what that formula is for finding slope? Careful. Okay, so that's the line equation with slope in it. What do we have? Rise over run is one way to think about it. Do you remember an equation for that so that we can write it down, an equation? Right, so this is slope. Visually, we're talking about rise over run. And from sort of an equation point of view, you might have written down something like y2 minus y1 over x2 minus x1 at some point in your past. Does that look familiar? Okay. You should have done this in lots of courses of algebra throughout high school and maybe even in junior high, depending on what you started with there. So what we're going to do is we're going to actually calculate some slopes of a particular line. So the line we're going to use, the equation we're going to use to start with is x cubed plus 2. Okay? So the first thing I want to do is I want to figure out what is the y value of this particular point at the x value of 1. So this is, they're calling it a here. I'm using the book's notation, and so you'll see up here that this says that x equal a. So the directions will start out like this in your homework, and then they tell you within the problem what the a value is. So this value of 1 is just an x value. So when x is 1, this is function notation. That's why it says f of x. All f of x's, if you'll remember, is another notation for writing y. Okay, so this is y equals. And the nice thing about the f of x notation is that I can replace where the x is with what the x value is that I want. So in this particular case, I want to talk about an x value of 1. So if I plug in an x value of 1, what will I get on this particular equation? 3. All right. So I know that this particular graph, and we'll graph it to start with just so that we can see it. If you go down into the y equals menu on your calculator, we're going to type in x cubed plus 2. And I'm just going to put this in a standard window. So if you're familiar at all with your calculator, you know how to do that. If you're not, or maybe you've forgotten, the way you can put this in a standard window is you can hit the zoom button, and you can hit zoom 6. The standard window actually puts it in a 10 by 10 window. That's not true. It goes from negative 10 to 10 on the x and the y. It's actually a 20 by 20 window. Okay? So that we can all kind of see the same picture of what's going on here. All right, so this is the graph that we've got. My x value that I'm looking at is an x value of 1. And at this x value of 1, you can see that I'm up here at 1, 2, 3. That's where we are in the graph. Everybody good so far? All right, so we've got a graph that looks, I don't know, a little bit like the ones that I drew over here. Okay, so it looks a little bit like this curve down here, right, where it's got a cubic look to it because it is a cubic equation. It's got a little bit of a curve going on there, and we're looking at this particular point at x equals 1, y equals 3. So we're going to be able to draw this line here. But what we're really going to do is not to draw the line, per se. It's really just to calculate what the slope of that line would have been. Make sense? So one of the points that we're going to use is we're going to use the point x equal 1, y equal 3, because that is the actual location of that point on the curve. Make sense? So we already talked about this equation right here, right? This is my equation for slope. So I need to have 2 sets of xy pairs, correct? And I have one of those sets already. It's x equal 1, y equal 3. Is everybody good so far? Okay. I need another point. Well, what we're going to do is we're going to choose points that are really close to the point of 3, of x value 3, and then we're going to let that point get even closer. Okay? So visually what you're wanting to imagine is you're wanting to imagine, and I'll take my other graph because I have it on here, you're wanting to take this curve right here, and you're wanting to have these points become very close together. Because if the points are very, very close together, it starts to look an awful lot like a tangent line, right? Because the points get very close together. So if you imagine on this curve right here, that now the point is right here, and you're drawing this line. The closer the 2 points are together, the closer it becomes to looking like the tangent line. So that's what we're going to do, and we're going to do that by using particular x values that are very close to the x value of 3. So in particular, the first x value we're going to use is 3.1. Then I'm going to use 3.01 and 3.001. Those points are getting closer to the x value of 3, right? Yes. Oh, it was 1, wasn't it? That's why some of you are looking at me funny. You're right. I'm sorry. 1. Let's try the right number here. 1.1. I'm sorry. I was looking at the wrong value. All right. Does that make everybody happier? Oh, it makes me happier too. Thank you so much. Please let me know when I make mistakes because it happens. So when we put in the x value of 1 originally, you just put it in and you guys figured it out really quickly. It was simple, right? The more messy that the equation or the value gets, like 1.001, and then you're going to cube it, and then you're going to add 3 to it or 2 to it, that's a little bit messier. You may not want to do it by hand, and depending on what the equation is, it might even be too messy that you can't do it by hand. Like what if it's a square root, or what if it's a trig function? We're going to do a trig function in a minute. So let you take a look at your calculator if you aren't aware of how to do a few things on here. We're going to make you aware of them. So what I'd like for you to do first is to make sure that your table is set up properly in order to do what I'm about to do, okay? So you're going to hit second window, and you should get a screen that looks something like this, right here, if you're using this particular version of calculator anyway. Now, it may not have all the same numbers written in the same places. It may not have the same thing highlighted. What you need to make sure that you do have is you need to make sure that both of these say auto. I'm sorry, don't say auto. We're going to make them say ask. The first one say ask. So I'm going to go down, and I'm going to change the first one that says independent to say ask. What that's going to allow me to do is it's going to allow me to choose to enter a particular value into the table instead of it creating its own table for me. Because I really want to put in the value of 1.1. I don't really care what the value at 2 is. That's not the point I care about. So we're going to make sure that we allow the calculator to have us put the input in instead of it choosing the input. Once you've done that, you can hit second graph, and it will come up with a table that looks like this that should be completely empty unless you've put something in it yourself recently or something like that. If you do have something in it, like you have, I don't know, something like this in it, you can go up to each of them, you can hit delete one at a time. It'll delete them. These are the values we want. We want 1.1, 1.01, and 1.001. So I'm going to put them in. And that's the f of x value that we have that we're going to list right here on the screen. Okay? Now, over here, the other kind of neat thing is, or you'll notice, is this one right here, the last one on the entry here says 3.003. I have a feeling that there's a little bit more to it than that, and it just shortened it in some way. If you actually just arrow over to being on top of it, you can actually see what it actually is. So for the most part, when we're working inside of tables, we'll record things. I know it's going to feel a little bit cumbersome right now, but we'll record things to 6 decimal places, okay? So that we make sure when we're at the end that we don't end up getting an answer that's been rounded 3 times, and all of a sudden it doesn't really look quite like the right answer. All right, so the first value that we have up here, I'll go up to it to make sure, is 3.331. The second one is 3.03031. And then the last one is 3.003003. And then, of course, it has more after that, but we're just going to go with 6 decimal places. Everybody good so far? So your calculator can do a lot of that very quickly if you use the tables instead of you having to enter it in by hand. And the more you have to enter by hand, the longer it's going to take. So it's a nice feature. We're going to do one more thing while we're here, is that we're going to actually let the x value be close to the value 3 from the other side. So, sorry, not 3, 1. So if this was 1.1 and it was close to the x value but a little bit bigger than 1, what do you think might be nice to choose that would be a little bit smaller than 1?
0.999.
Right. So we're going to start with 0.9. 0.99, and then 0.999. And if we're still on the screen, the calculator, we can enter those as well and let it do the work for us. All right, so the first one at 0.9 has an f of x value of 2.729. The next one has a 2.97. 0299. And the last one says 2.99700, and then it'll be 3 because we will round the 2 up. If you don't round the 2 up, it's really not that big of a deal. It's not going to hurt things in the long run. But at least record 6 decimal places, and then you can round or not round in the end. It's not going to matter. Okay? All good? We haven't actually found what we're finding totally yet. We've just found the other 6, in this case, XY ordered pairs that we're going to use to find slope. Now, let's go back out in your calculator screen to the regular screen window. You guys told me a minute ago that this was my slope formula, right? And I know that I have an XY ordered pair where the X is 1 and the Y is 3. So I can put those in and it will stay the same every time. What's going to change is going to be the other XY pair for the other 6 points that I've selected. So my general term for what I'm going to be doing is I'm going to be putting in the calculator, the first y value is 3 minus something, and the something right here is going to be these different f of x values that we just calculated. And then we're going to put a division sign, and we're going to put another parenthesis, and we're going to do 1 minus, again, something. It's a different something this time, but it's going to be the x value that we used from our table. So back on our calculator screen, this is going to look something like this. I'm going to have 3 minus, because that's the y value, the first y value that I've listed, which is the 3.331. And I'm going to put division sign. I'm going to open another parenthesis. These parentheses are really important. Your calculator understands order of operations, which means if you leave those parentheses out, what it's going to do is it's going to divide the two terms in the middle first. I don't want it to divide the terms in the middle. I want it to subtract what's on top and subtract what's on bottom. So you have to tell your calculator that by using those parentheses. And then I've got 1 minus the first x value, which was 1.1. And if I key that in, I can press enter, and it calculates my first slope as 3.31. Okay, now you can type that all in again, but wouldn't it be nice if you didn't have to? All right, so your calculator has a feature where you don't have to type it all in again. If you hit the second key, and the little negative key that's down on the bottom by the enter key, it says ANS above it in yellow, or in a different color usually like this. I hit the wrong thing. Second and enter. There we go. Hit second and enter. It will pull up the last entry that you created. So it pulls it up just like it is. But we don't really want the exact same entry, right? What we want is we want to change the 3.331 to 3.030. And I'm missing some spaces now, right? So you can enter those by hitting second and the delete key, which allows you to insert the last 1. So 3.03031. And then at the end, I've got 1.01, and I can hit enter. And my slope between these two sets of points is 3.031. Okay, so far so good? Okay, so let's go through that process again. I hit second and enter, pulls up the last line. And then I want to change the 3.03031 to say 3.00300. And again, I don't have enough spaces, so I'm going to hit second, insert, and put another 3 there. So second delete or second insert allows you to enter a spot. I'm going through a lot of calculator stuff really quickly. Come see me if I'm losing you. I promise we'll work it out. It's not that complicated. It's just keystrokes. And then the last one is 1.001. So this last slope that we just calculated is 3.003. What's it look like the slope is getting close to? 3. Looks like it's getting close to 3. So we're going to check from the other direction and see if that's really what's happening. And we'll use the other values. So I'm going to do the same thing again with my 0.9 kinds of values now. I'm going to hit second enter. The first y value that I need to enter is 2.729. You can hit delete if you want, but you could also just make them all 0 so that we don't have to reinsert anything. It'll save us some keystrokes later. And then the x value is 0.9. And again, if you want, you can put zeros in there if you want, or you can delete them out. So the first slope that we actually get on this first one from the 0.9 side is actually 2.71. I mean, it's not that off of 3, but it's further away from 3 than any of the other ones were, right? Definitely. Okay, let's try it again. But we're going to use 2.970299 and 0.99. I get a slope of 2.9701. That's closer to 3, right? One more time. I'm going to put in 2.997003 and then 0.999. And I have 2.997. Is it also getting close to 3? Yeah, it is. And I'm not proving that this is becoming 3, but we're just arguing that that's what it appears to be happening. This is an estimation, right? It says estimate. Now, the reality is this actually is the value. It really is 3. That's what the slope is. But we haven't proved it. Okay? We've just argued that that seems reasonable, that they're all getting close to 3. Does that make sense? All right, so it would be helpful for you at some point in here to write down that these values are actually the slope. So this slope, and actually I probably should have used approximation, is approximately 3 because we haven't really proved that it's 3. We've just estimated. Okay? So make sure you answer the question that's asked. The tables are fabulous, but we want to make sure that you know what the tables mean. That is, that you're able to see what your table is doing and tell me, yes, I'm telling you now that the slope is approximately 3 from my table. So far, so good? All right, we're going to try another one. Same direction, same idea, but now we're going to use a trig function. And the trig function is the tangent function. You may remember what the tangent function looks like. I'm going to go into y equals. I'm going to graph it. So this is tangent of x. And I'm going to use the trig viewing window, which is zoom 7 for trig, for us to see the trig window. So if you've taken trig recently, and most of you've probably taken some kind of trig recently. Yes? All right. One of the things I want to remind you of on this graph right here that you're seeing is these vertical lines, they're not really here. Some of your calculators may not even be putting them in there, but some of the calculators do. They're trying to connect everything. So they're trying to connect something that's way up high at the top and something that's way down at the bottom, and the reality is they don't connect. Those are actually asymptotes. Remember that, okay? So that's not really part of the graph, but the curved parts in between that look like a repeated function, cyclic is what you call it in trig, that's the tangent function. Now, the tangent graph that we're going, or the point that we're going to be looking at is the point at pi over 4. Just for our reference, because pi over 4, I mean, like, what am I going to use? That's not exactly x equal 1. So how am I going to choose then the correct values? We're going to do an approximation for that in a minute. But let's actually just plug in at the pi over 4 and see what happens. So if you go into your table, you can delete out what you have. Just delete all 6 of those. And you can actually type in pi divided by 4. And it's going to approximate it for us, which we're going to use that in a minute. But what we're interested in right now is the y value. So the x value is pi over 4. The y value is 1. So we put in pi fourths, and it gave us 1. Okay, good on that? You should remember that from the unit circle. If you don't, I'm not going to deal with that today. We'll talk about unit circle stuff later when it is important. Right now, we're not dealing with it. Okay.
I've got the x factor on y.
Check and make sure you're in radian mode. And if anybody else's is not working, that's probably what's wrong too. And for any calculus class that you're in, you want to be in radians anyway, so you won't need to change it back.
Is that under mode?
Yes.
Yep, I was looking for
Perfect. All right. I'm going to come over here and take a look at this x value. If you take a look at this pi over 4 x value is approximately 0.785398. We're going to get close to that value a little bit bigger and close to that value a little bit smaller. And when you're working on this by yourself, you may not choose the same x values I choose, and that's perfectly fine, especially in this case. The last one, it seemed reasonable to choose 0.9 and 1.1. Here, there isn't really a standard what should I choose kind of thing going on. I'm going to choose 0.78 to start with. That is smaller than 0.785398, right? Okay. And then just for fun, I'm going to go then with, after that, 0.785. Also smaller, but getting closer, correct? What do you think I might choose next?
75.
I'm going to go with 785.3. 2 would be fine. You could use 2. I'm going to use 3 just because it's the next number of the actual decimal expansion I have. So I know it's still smaller, right? But it's getting closer as well. The other side of this is maybe not quite as clean to even write down as the ones we just did. I need something bigger than 785.398. I'm going to go with 789. Is that okay? Or 79, actually, is what I'm going to say. 79. That's bigger than 785, right? Okay. And then the next thing I'm going to do is I'm going to try maybe 789. That's also still bigger than 785, but it's smaller than 79, right? And we're going to do the same thing one more time. I'm going to do 785.9. This one, 785 is smaller. I mean, is smaller than 789. Yes, but it's still bigger than that number. If you don't like my numbers, that's okay. But the idea of how to choose them is simply that it's bigger than what you wanted, in this case, but getting closer to it. So you can pick different values if there's nothing special about the numbers I picked. But what we're going to do is we're going to enter them in the calculator and let the calculator tell us the corresponding y value for these. So, 0.78, 0.785, 0.7853, 0.79, 789, and 7859. And then I'm going to arrow over on top of them and write each one of them down with 6 decimal places. Okay, 989.261, 999.204, or you could go with 203, that would be fine. 999.804, 1.009246, 1.007, you can write 230 or 229 is fine. I've been rounding all mine, so I'll round this one to 230. Last but not least, 1.001004. This is tedious, right? These problems are not, it's not a huge assignment. If you look at the list at the bottom, you guys see that homework list at the very bottom of your page? There's not that many of them on there, right? But this is tedious. It takes a little while to get them all written down. All right, so what we're going to do next then is calculate those slopes. So back in your regular screen, you know you have one xy pair, which is the pi over 4 and the 1. The other ones are all listed in your table. So what we're going to be putting in our calculator is we're going to put in the the y value, which is 1 minus, and then we'll have a y value divided by the x value, and I'm actually going to enter this pi over 4 because I can. I might as well use the exact value. And then minus the x value that's approximated that I've been using. So we're going to go with 1 minus, and we'll do the first one, which is 0.989261. Close the parenthesis and divide. And then we have pi over 4 minus the first x value, which is 0.78. And it's telling me that I have 1.989380. Okay, I'll do the other one now, or the next one I should say. So I have 999.204. Remember I did second enter to pull it up again. And I'm doing 785. So this is 1.99 0.9179. Second enter pulls it up. All of these have 6 values on the f of x value, so that's actually kind of nice. 999,804, and then 7853. And this number is 1.996671. What does it look like those slope values are getting close to? They look like they're getting really close to the number 2. Let's try it from the other side then and see what happens. All right, so we're going to go with 1.00924, and then I'm going to have to do an entry of an insert for 6. And then my x value is 7, 9. And I'll just do zeros, zero those out. This particular slope value says 2.009198 if I round. 197 if you don't, and it's okay if you don't. You'll get to the same result. So next one, 1.007230. X value is 789. This says 2.007309. And then we've got one more to do. 1.001004. 7859. And this value is 2.000651. What do you think? Is it 2?
Yep.
Yeah, looks like 2 to me. All right, so all of these appear to be getting closer to the value of 2. So we will say that our approximation, our guess, our estimation is that the slope is approximately 2. Good to go? All right, so this is one application, one thing that we're going to be working in calculus and doing. We're not going to do it with tables forever, all right? But this is a numerical approximation of how to find the slope between 2 sets of points, all right? And then thereby estimate or approximate the slope at one particular point. We're going to do one more application. This application is an application of finding the distance or the length of a curve. So what we're going to do is we're going to estimate the length of a curve at y of the curve of y equal f of x on the interval using n equal 4 and n equal 8 line segments. So if you will imagine the idea being, in fact, we'll graph it to start with so we can talk about it. The equation that we're working with here is the square root of x plus 1. And I'm still in the trig window right now because that's what we were just using. So I'm going to hit zoom 6 again to standardize the window to be that -10 to 10 window. So this is the standard curve for square root, and it's shifted 1 unit to the left because of that plus 1 underneath the radical. What we'd like to do is we'd like to find the length of this curve between the x value of 0 and 3, and we're going to do it by making little pieces of line segments, okay? So imagine if you had only a ruler and you were trying to do this. Well, a ruler's straight. That's not helpful if the image is actually a curved image, right? Now, you probably have other images of how you would do this. You might take a string and string it along there, something like that. But if you only had the ability to measure in straight line segments, that's what we're going to actually use to approximate this. And this is actually what your computer would do if you told it to do this using calculus. It wouldn't use calculus. It would use a numerical approximation anyway. Okay? So we're going to do this with 4 line segments. All right, so to start with, we need to figure out what the x values would be. Obviously, the segment from 0 to 3 is not nicely divisible by 4. It would have been better if I'd chosen 0 to 4, wouldn't it? Man, that would have been friendlier. But I chose something because I wanted you to see it doesn't really make any difference. So if you were talking about the distance between 0 and 3, and you divide it into 4 line segments or 4 pieces, you could actually just take your 3 and divide by 4, of course, right? And you have 0.75. So the first x value we're going to put in here is the x value of 0 because we're starting at the x value of 0. And our second x value that we will end with, sort of if we were like imagining putting the ruler on the curve, is we're going to end at the x value of 0.75. So each of our line segments are going to be 0.75 long. So now if I start at 0.75 and go another 0.75, where will I end? 1.5. Right? 0.75 plus 0.75. It's 1.5. We're going to do it again. We're going to start now at 1.5 and go another 0.5 long. I'm sorry, 0.75 long, and where we're going to end. Good, 2.25. Now you guys are on the roll. One more. If we start at 2.25 and we go 0.75 more, we end at 3, and that's how we know we did it right, because that's what we were supposed to end at, right? Start at 0, end at 3. All good? Excellent. Well, I need to know the f of x values. You guys know how to calculate those. We already put the y equals square root into the calculator. You already know how to do your table. So we're going to put these particular 5 x values in our table. 0, 0.75, 1.5, 2.25, and 3. And your calculator spits out for you, of course, the corresponding y values. All right, so we're going to write those y values down. I have 1. I have 1.32287. And this time, just to show you it doesn't make any difference, I'm just going to keep the numbers as they are. I'm not going to do any rounding. I'm just going to write the first 6 decimals, which is fine. The next one is 1.581138, if I don't round. All right, so at 2.25, I've got 1.8027775, and at x equals 3, it's the very nice x value, or y value of 2. All right, so we're not calculating slope here, though, right? What are we trying to find? Length, which is also called distance. Do you remember a formula for distance?
It's like a crazy one, right?
It's got a square root in it. I don't know if that calls it crazy, but it's harder than the slope formula. I mean, in terms of calculation purposes.
Isn't it like something minus something squared plus something minus something squared?
Yeah, there's some somethings in there, and my screen just completely went off.